I just want to give a quick introduction and welcome everyone to the USGS seminar series. And I will be passing on the introductions to Tina, but we are very lucky to have Judy Fierstein come and give this talk here. And just to let you know, we do have a public talk going on at the museum tonight at 7 p.m. There are a lot of other events scheduled throughout the summer to start commemorating the anniversary of the Novarupta Katmai eruption in 1912. This is 100 years later. There are various fact sheets, cards, and other information up here. If at some time after Judy finishes, please feel free to take any information that you like. And I'll go ahead and pass this on to Tina.
Thanks for that. Yeah, thank you everyone for coming. This really is an exciting day. Sorry for those of you behind the pole there. It's with great pleasure that I get to introduce Judy Fierstein, who is a USGS colleague from Menlo Park, California, a research geologist who has been working with USGS since 1980. And I realized in preparing for this that I first met Judy in 1982, actually out in the valley of 10,000 Smokes at the Big Mountain Cabin, after my first very arduous backpack into the valley with Terry Keith. So this is a great 32 years later return to introducing my friend and colleague. Judy is the world's expert on the Great Eruption of 1912. And today we're going to be hearing some highlights of her 32 years of work out in the valley. Judy has worked side by side with Wes Hildreth, another USGS colleague that many of us know, and many of the world's leading volcanologists that she's managed to bring out into the valley, to focus mainly on deciphering details of the Great 1912 eruption. Judy's done a lot of very, very detailed mapping of the deposits from 1912, teasing out fine details about the timing of emplacement of ashfall and ash flow. And many of the insights into the mechanisms of these processes have really profoundly influenced how volcanologists now view large explosive eruptions worldwide. Judy started with the USGS in 1980, as I mentioned, and this was soon after the Mount St. Helens eruption. Her first summer at Katmai was in 1980. She started as a maggot intern, and as I said, has been working out of Menlo Park with Wes and others since then. In addition to her work at Katmai on the Katmai eruption, she's also an expert on the eruptive histories of all the Katmai area volcanoes, from Kaguyak down to Alagagchak. I don't know how she's found the time and energy in her career, but she's also done a number of very detailed mapping and hazard analyses of volcanoes in the Cascades and in the high Andes of South America. She's also an accomplished mountaineer, and as part of her world experience has climbed many tall peaks, including Aconcagua and the north peak of Mount Everest. So she has many achievements both in geology and outside. She's a fellow of the Geological Society of America, and receives a lot of awards from peers both domestically and internationally. With that, I'll turn it over to Judy for the first in a series of talks. After today and tonight here in Anchorage, she's going to Fairbanks to do a repeat performance, and then on Kodiak Island on Thursday to speak at the Baranoff Museum. And Kodiak, of course, ground zero for huge accumulation of ashfall. Judy.
Well, that's me, I guess. Let's see. The hardest part about preparing for this talk was figuring out what I could say to keep it to about an hour. But for anybody who wants more information, this is coming out soon. It's a professional paper from the USGS, and it summarizes not just what we've learned over the last 30-odd years, but also the development of the studies in the Valley of 10,000 Smokes, the sort of cultural and scientific background for all the studies, all sorts of things in here will be USGS publication. Well, to embellish Tina's stories a little bit, 32 years ago, just graduated from college, I caught a ride from UC Santa Cruz, where I was going to school, over to the USGS with Chris Nye, who some of you know. And he was going to the survey to talk to a person on his thesis committee. And I planned to knock on doors with everybody in what we called then the Alaska branch, because I wanted to go to Alaska. Who doesn't? I was looking for a summer job, and while I was knocking on doors, Chris asked his thesis advisor if maybe he needed a summer field assistant, and he said, oh, I'll talk to her. And so I met Wes Hildreth, He did offer me the job, but not in Alaska. We were supposed to map Mount Adams, which is another volcano in Washington due east of St. Helens. And so I began working in the USGS in March. And 2 months later, Mount St. Helens erupted, and it was a pretty big one. The Forest Service closed all the access roads to Mount Adams for the summer, so just by lucky circumstance, the effects from one Pleiadian eruption started me on my career to work on another, even bigger one. So instead of Mount Adams, we went to a place that Wes had just begun to explore, the Valley of 10,000 Smokes, Katmai National Park. And I ended up in Alaska after all. So 5 months into my new job, we flew from San Francisco to Anchorage and on to King Salmon on one of those rare days when I could see every snow-topped peak from Seattle to Alaska. We took a float plane from King Salmon to Brooks Camp. We walked to the falls there and saw the bears fishing. This was well before the viewing platform. It's when you're clapping and yo bear really made a difference. And we caught a ride to the end of the 23-mile road in the park to what's called the Overlook Cabin. They have a new one there now. And from there, we had a wonderful view up the Valley of 10,000 Smokes toward Mount Katmai. And I looked over where we would be spending the next 6 weeks. And that was a summer of many firsts for me. It was my first ever backpacking trip. We brought with us everything that we'd need for 6 weeks, and it was just the two of us. And so began a lifelong friendship and a productive working partnership with Wes Hilder. Well, what a place. It was there that I learned that one of the things I like least is cold feet. But there was much to learn. So the event that created the Valley of 10,000 Smokes and Katmai caldera was the most voluminous of the 20th century. It exploded on between 6th and 8th of June, 1912, from a new volcano, later named Novarupta. It sent ash around the world. It was more ash than from any other, from all the other historical eruptions in Alaska combined, and it devastated areas hundreds of miles away. The eruption lasted for 3 days, and it focused scientific attention on the hot ash flows that caused the 10,000 smokes. But its significance for the developing science of volcanology involved a lot more than just size. So just for perspective, let's take a quick look at the context of this big event. Well, Alaska was then and is now in a remote area. Katmai is in a remote area of Alaska. Okay. Anyway, we'll go here to the Dora. On June 6th, 1912, it was making its usual mail run from Uyak to Kodiak. And if there was anything unusual about the day, it was that it was clear in the Shelkof Strait, and the ship traveled all morning under clear skies. So, in terms of the geographic context, the geology, microscopic petrography was pretty sophisticated by then. And also by 1912, major element analyses were pretty standard, but little was known about magma sources. There was no Bowen's reaction series yet, and the hot topic of the day was how do different magmas evolve. The awareness of plate tectonics was about half a century in the future. The seismology had come a long way by 1912, but there was only one seismograph in Alaska, and that was in Sitka at the time. There were about 30 others distributed around the world. In terms of volcanology, it was recognized that fissure eruptions were different than central vent eruptions, and it was also realized that gas was an important driver in explosive eruptions. It was recognized that incandescent clouds or pyroclastic flows are sometimes associated with lava eruptions, but what was not appreciated was the scale, the abundance, the nature, the origin, and the lithologic variability of ignimbrites, or pyroclastic flows, pyroclastic density currents. They were poorly understood during the early investigations of Katmai. The principal comparators were pretty small and were making, like the one at Soufriere and the directed blast from Montpellier in 1902. Krakatoa would have been a good comparison, but most of the 1883 deposits were underwater, and that was also true of the 79 eruption of Vesuvius. So most of the studies on those two places look mostly at the fault deposits. And calderas were also poorly understood. Basically at the stage where people would use phrases like Krakatoa blew up. The idea of collapse hadn't taken hold yet. Well, funding sources. Funding sources weren't quite well established. There was no NSF. And many volcano studies were funded independently from generous individuals. The USGS did support research and had for about 30 years, but it was modest, and there was no secure congressional funding in 1912. So, in 1912, it was the research committee of the National Geographic Society who sponsored Martin's first trip in 1912 to Katmai. He was actually a U.S. geologist. And they also sponsored all the Griggs expeditions between 1915 and 1919. So, a century ago, the field of volcanology was in its infancy. There were many things from this eruption that had never been seen, and they weren't very well understood. Subsequent research there has taught us a lot about processes and hazards associated with such large explosive events. And now, 100 years later, we look carefully at that event and consider, well, what would happen if a similar one erupted today? Okay, so today we're going to look at not only what happened during those 3 days in 1912, but also what we've learned by studying them so closely, and how they've remained scientifically important for 100 years. But before we consider what was happening at the vent, and here's the Dora part, we're going to take a brief look at the eruption from a distance. On June 6, 1912, the Dora was traveling from Yuyak to Kodiak on its normal run, and they had already made the turn into Kodiak when they heard a really big explosion. And they saw a rising eruption column about 1 o'clock in the afternoon. The eruption column rose quickly, and it spread rapidly, and it overtook the ship about 3 or 4 in the afternoon. Ash began falling on the deck about 6 in the evening, and the ship was enveloped in complete darkness soon after that. The air, thick with ash, was stifling. Rather than risk landing at Kodiak, the captain decided to head out to sea. There was thunder and lightning and birds falling out of the sky and landing on the deck. The cloud quickly reached an altitude of 32 kilometers, and within 4 hours, ash from the huge volcanic eruption began to fall on the village of Kodiak, 170 kilometers to the southeast. The ash cloud was seen for hundreds of miles and was carried by stratospheric winds spread around the world. Actual ashfall was reported as far as the Mediterranean. By the end of the eruption 3 days later, on June 9th, the ash cloud, now thousands of miles across, shrouded southern Alaska and western Canada, and sulfurous ash was falling on Vancouver, BC, and Seattle in Washington. The next day, the cloud passed over Virginia, and by the 17th, it reached Algeria. Now, this great quantity of ash caused unusually brilliant sunsets, and by shielding the sun's rays, lowered the average temperatures by about 1 degree centigrade in the northern hemisphere for more than a year. Well, during the 3 days of the eruption, June 6th, 7th, and 8th, falling ash and sulfur dioxide gas immobilized the population of Kodiak. It was dark. Many complained of sore eyes, breathing problems, water became undrinkable, and there were no radio communications. Ships couldn't dock because they couldn't see, and the people were just cut off from the rest of the world. Roofs in Kodiak collapsed under the weight of about 30 centimeters of ash. Buildings were hit by avalanches that rushed down from the nearby hill slopes, and other structures burned after being struck by lightning from the ash cloud. The similar conditions prevailed elsewhere in southern Alaska, and several villages were abandoned forever. Ash and acid rain affected more than just people, too. Bears and other large animals were blinded by ash, and they starved because the plants they ate and the small animals they ate were all killed by the ash. There were millions of dead birds that had been blinded and coated by volcanic ash. Even mussels, insect larvae, kelp, and the fish that fed upon all those things died in the ash-choked waters. Alaska's salmon fishing industry was especially hard hit, especially between 1915 and 1919, because the salmon in 1912 starved in the ashy waters and they couldn't spawn. So clearly, the effects of the 1912 eruption were far-reaching and it caught people's attention. George C. Martin of the USGS interviewed many eruption refugees just a month after the big event. And he compiled comprehensive accounts of the eruption impacts on both sides of Shelikof Strait. He heard villagers' reports of strong earthquakes as much as 5 days before the eruption, which prompted them to leave their homes, which is a good thing because no people died during that event. But with all that, no one knew what happened in the immediate vicinity of the volcano. No living thing survived near the vent itself. It wasn't until 4 years later that Robert F. Griggs, outfitted by the National Geographic Society, hiked across Katmai Pass to the heart of the eruption area. And that's where he discovered and named Novarupta, meaning newly erupted, and the thousands of columns of steam and ash that he called the Valley of 10,000 Smokes. And he also saw the Katmai caldera. So as Griggs began to publicize his discoveries, the world learned that an eruption of historic proportions had occurred in this remote area of Alaska. Well, as part of the Aleutian Arc, Novarupta and Katmai have many active volcanic neighbors. All of the nearby volcanoes have active vents except for Alaska Chapter. So just so you know where things are, this is a simplified geologic map of the Valley of 10,000 Smokes, which is the tan color. It has Katmai, Trident, McGeek, and Martin on the arc crest, and Griggs is slightly behind it. The magnitude and the volume at Novarupta in 1912 were clearly exceptional, far larger than any other historical eruption anywhere in North America. But there are several other things about this eruption that have made this place so important in shaping our thinking about large explosive events. For the first time in recorded history, a great explosive eruption deposited its pyroclastic flows on the land instead of in the sea, like at Krakatoa. So for the first time, they could be studied in detail. It was one of the few places where it was recognized that a whole range of magma compositions erupted together. In 1912, one of the hottest topics in geology was how do evolved magmas originate. The unusual occurrence of co-erupted rhyolite, dacite, and andesite began debates in the geologic community about how these different magmas could all be erupting from one system. And the third thing so unique about this eruption is that the vent from which the vent is still largely preserved. When the early investigators, Clarence Fenner and Robert Griggs, first reached the summit of Katmai in 1916, the cliffs that surround the summit crater were fresh and glacier-free. There were vigorous fumaroles that ringed the caldera floor around the shallow lake. And in 1923, there was no lake at all. So they understandably thought that Mount Katmai was the vent for all the pumice and ash. But it wasn't until 1953 did the newly hired UC Berkeley professor, Garnis Curtis, measure ash thicknesses that made isopack maps that clearly showed that Novarupta, not Katmai, was the vent for all the pumice and ash from 1912. Mount Katmai did collapse during the eruption because most of the magma had been stored beneath it. But all the magma vented, or almost all the magma vented at Novarupta 10 kilometers away. So understanding this underground plumbing system that permitted this to happen spurred debate that continues today. So it's been these three things: the on-land pyroclastic flows, the wide compositional range, and deposits preserved right up to the vent that enabled us to make so much progress here and understanding better eruptive and emplacement processes of large explosive events. Curtis started the ball rolling by clarifying many things about the 1912 eruption, of course most importantly where the vent was. But after that, many advances were made in volcanology in general. And this led up to the perfect storm, so to speak. So the next step here began with a detailed stratigraphic documentation that we did in the 1980s, just in time to take advantage of what others were finding elsewhere, and to use some of the unique features of this eruption to contribute to the growing field. We've spent a lot of time measuring stratigraphic sections from Kodiak to Pumice. And the red dots here mark the section locations right around the Novarupta vent, which have been especially useful in figuring out what happened in 1912. When a big explosion like this happens, and then the caldera collapses, much of what we've measured at Novarupta is no longer preserved. This is the eruption column from Pinatubo, which erupted only 21 years ago. And although the second largest in the 20th century, it was still half the volume of Novarupta. But you can see in the photo here that as at Novarupta, so much came out of the vent at once that ejecta went up, down, and out all at the same time. As the central part was thrust up to the stratosphere, the margins of the Plinian column collapsed locally. So the resulting ultra-proximal deposits are hybrids of all these contemporaneous processes. The collapsing margins flooded the vent area, flowing down the surrounding valleys. At Novarupta, the pyroclastic flows filled the valleys as deep as a couple hundred meters. Some of the ejecta went out, never part of the high plume, but rather just hurled out of the way on a ballistic trajectory. This one, a lot bigger than me, I'm the scale, is just over a kilometer from the vent. Ash and pumice in the central part, the first Plinian eruption, went up to about 32 kilometers and were distributed widely by regional and stratospheric winds and deposited as ashfall. The fallout is nearly 12 meters thick here, about 4 kilometers northeast of Novarupta. And the layering that you see in general reflects the accumulation of the pumice bit by bit. Some of the pronounced lines you see reflect changing conditions at the vent, with some starts and stops in the eruption, which we'll talk about in a few minutes. The coarse clasts that typify the fall deposit here are a lot finer 12 kilometers further away, where the same deposit, still layered, is less than a meter thick. One of the things I discovered while measuring such sections is that the deposits change in character not just downhill, but they change differently from one azimuth to another. Well, this makes a lot of sense, but when I was first starting, no one published that sort of stuff, and no one talked about it. Ash thickness and ash and pumice sizes are important ways we characterize the deposits when we compare them from one place to another in areas near and far from the vent. So as you've seen already, the ash was widely distributed. In order to measure its thickness far from the vent, Jim Riley and I hired a fishing boat 2 different summers to look for ash on both sides of Shellicop Strait. And thanks to Captain Eric Stirrup and first mate Hank Pennington, we made it there and back again in spite of some stormy weather. But I must say that by the time I was done, I swore I'd never take a 50-foot fishing boat across Shellicop Strait again. Well, those thicknesses and the ones we measured closer to the vent are compiled on this map, where distribution and thickness of the ash is shown by the red lines. Novarupta is the yellow star. And these isopacks are elongate and reflect that the wind blew strongly southeastward. You can see the 30-centimeter isopack includes Kodiak, 170 kilometers southeast of Novarupta. It's using the distribution pattern and the thickness of the ash that we calculate the 3-day eruption in total produced just over 17 cubic kilometers of pumice and ash as fallout. If that were compressed back into dense magma, that would be about 6.5 cubic kilometers of magma. There was another 11 cubic kilometers of pumice and ash erupted as ash flows. Well, another really important part in figuring out the eruption events are the records of ashfall at Kodiak. It was reported that the heaviest ashfall came in 3 periods over the 3 days. So we call them episodes 1, 2, and 3. Each have a few hours break in between. Remember, the Dora spotted the first eruption column at 1 p.m. But it took several hours for that ash to reach Kodiak. So you can see on the diagram that the 3 periods of ashfall on Kodiak were about 4 hours later than the corresponding eruptions at the vent. So, ash was falling at Kodiak between 5 in the evening on June 6th and 9 a.m. on the 7th. And it started falling again at noon and fell until about 2:30 the next day. And the third ash began the evening of June 8th. But June 9th dawned clear. So ash intervals at Kodiak are really important constraints on the timing of the 1912 events. Well, we looked at the timing of ash intervals at Kodiak. Now look at the left side of the diagram. This is the chronology of the entire eruption. For the moment, focus on 3 things. Number 1, each episode includes 2 to 3 fall layers, called layers A through H, first named by Curtis. Number 2, nearly all the flows that filled the Valley of 10,000 Smokes erupted during the first episode. So they were over before 9 a.m. on June 7th. And number 3, episodes 2 and 3 were largely ashfall with no large ash flows. On this aerial photo, if you know what to look for, you actually can see a good deal of the general eruption story. You're looking southeast toward Shelikof Strait and Kodiak Island, right along the main downwind axis for the fallout distribution. Episode 1 began with a big blast that plastered all the near-vent slopes that you see with high-energy ash flows. The eruption rate was so great that some of the ash and pumice went upward into the towering eruption column to be deposited as a regional fall, and some of it flooded the vent area as ash flows. Episode 1 left a 2-kilometer-wide depression filled with pumice and ash from its own eruption. I've circled it in yellow. Fault scarps caused by the collapse in subsidence in 1912, including Falling Mountain on the right, encircled the area that was the vent for the first day of the eruption. By the time that first phase was over, nearly 20 cubic kilometers of new pumice and ash filled the surrounding valleys and covered the landscape. Nearly half of that was erupted as fallout, and the other half deposited as ash flows. Within the larger vent, the subsequent eruptions bored through the already partly consolidated deposits of episode 1 through a smaller vent that produced the ash falls of the next 2 days. Nearly all of the 8 cubic kilometers that erupted during this time was dispersed as regional fall. There were minor ash flows, but they didn't go very far. So these eruptions, episodes 2 and 3, also built a ring of pumice-rich ejecta around their smaller vent, which we informally call the turtle. It's shaded in yellow. And in the end, when all the explosive eruption was over and the people in Kodiak could finally breathe again, the last bit of magma extruded at the vent as the Novarupta lava dome. So we go back to this diagram, which shows the sequence of events as represented by the different fall layers, A through H, that accumulated one on top of the other throughout 3 eruptive episodes. The lulls in the falling ash on Kodiak were actual breaks in the eruption, and only then was it calm enough for the fine ash to settle near the vent. So the gray bands in the diagram, labeled EMH, are the fine dust that accumulated near the vent during those relatively quieter times. Once after episode 2, and again after episode 3 when the eruption was all over. Those fine ash layers, the arrows point to them in the photos, are distinctive, and they were important markers for us as we put together this eruptive sequence and measured ash sections from one place to another. Well, by now I've given you a general overview of the sequence of events. In order to decipher what was happening to the vent, happening at the vent during these eruptions, we're going to look carefully at the surrounding deposits. That's Colin Wilson, for those who know him. Some of what we do is we sit them to characterize their drain sites. In the previous slide, Colin was actually counting pumice clasts, counting the different types of pumice clasts. The key to understanding the sequence of events relies on being able to distinguish the 3 pumice types: the rhyolite, the dacite, and the andesite. So although they were ejected together throughout most of the eruptions, their relative proportions varied with time. So it's these variations that we use to track the dispersal, the character, and the thickness of each layer, both around the vent and in more distal locations. And that information was pieced together to figure out what happened during the 3 days in 1912. So not only can we put the episodes into a real time frame by using the recorded ash at Kodiak, but we can connect the fallout on Kodiak with what was erupting at the vent by comparing the compositions of ash and pumice in both places. So because this compositional sequence was so important in the detective work that went into figuring out what happened during the eruption, we're going to take a look at it more carefully now. Well, episode 1 began with widespread dispersal of purely rhyolitic fallout. Fallout was called layer A, and contemporaneous all rhyolite ash flows. This is one of the few places historically that have erupted such a large volume of high silica rhyolite. After a few hours, andesite and dacite magma joined in, marking the beginning of what we call layer B. And I'll point out that layer B has a few sublayers to it. In this photo, about 3 miles southeast of the vent, the fallout is intercalated with ash flows in both the all rhyolite and in the mixed rhyolite, dacite, andesite deposits. So the 40 centimeters of compositionally mixed fallout flow here represents the same time interval there, about 16 kilometers in the opposite direction. So this is in the lower part of the Valley of 10,000 Smokes, where most of the ash flows accumulated. It's about 12 meters thick. So you wouldn't necessarily, at first glance, connect those 2 types of deposits, but it's the compositional proportions that are the same in each that makes that possible. So, looking a little more closely, pumice proportions in the fallout of layer B change from more than 99% rhyolite at its base to only about 15% at the top, matching the progressive shifts in rhyolite, dacite, and andesite. The pumice proportions in the main sequence of the ash flow pulses, or the packages of flows, and placed concurrently in the Valley of 10,000 Smokes. And the color change in these ash flows shows that change in composition pretty well. Well, by 9 a.m. or so on June 7th, the emplacement of the ash flows was over, and ashfall stopped at Kodiak for a short time. Episode 1 lasted those 16 hours and produced almost all of the Valley of 10,000 Smokes, the ash flows. That's about 11 cubic kilometers, and roughly half of the fall deposits, nearly 9 cubic kilometers. So we're going to move on to episodes 2 and 3, which were similar to one another. Each of them began after an eruptive lull, and then they erupted from the smaller vent I showed you, nested inside the larger one of episode 1. Each deposited widespread fall layers, layers C, D, and F, G, and they were almost entirely basaltic. Layer E is the fine ash that settled between them. And in contrast to episode 1, which produced the big ash flows of the Valley of 10,000 Smokes, almost all the volume of these deposits were fallout. But notice the fine-grained layer that separates layers C from D here. That thin layer here, about 4 kilometers from the vent, is just the fine dust that got winnowed out of small ash flows, like here, that erupted at the same time as the fall, but never made it out of the immediate vent area. So these small ash deposits are only seen, these small ash flow deposits are only seen near the vent. You can see Novarupta peeking up at the top of the picture. Even during the lull between episodes 2 and 3, which was the longest break, some of these small ash flows were deposited from small explosions. So it's these ash flows in the area around Novarupta that show that the vent remained unsettled even while residents of Kodiak were hoping it would blow over. These sorts of details are preserved only because most of the collapse occurred at Mount Katmai. Other details preserved in the deposits near the vent have enabled us to connect the eruption of the compositionally variable fall deposits during episode 1 with the compositionally similar flow deposits that were erupted at the same time. So by counting the pumice types in the deposits, we can correlate the fall and flow deposits with one another, even though in character they look pretty different. And we can correlate deposits near the vent with those further away. And for the first time, it was documented unequivocally that a big Plinian eruption column could produce both fall and flow from the same time, at the same time, from the same sustained Plinian column. Previous ideas that the entire column had to collapse in order to generate a pyroclastic flow were shown to be incorrect. So that same synchronous fall-flow relationship has been shown in other places since then, and this changes how we view potential hazards from such eruptions. Well, this diagram summarizes the changing proportions in the pumice types throughout episode 1. The flow deposits are on the left and the fall deposits are on the right. The colors on the left represent the changing proportions of pumice types in the ash flow deposits. They're 100% pure rhyolite at the bottom with progressively less rhyolite toward the top, just like the fall deposits. Well, the Valley of 10,000 Smokes was once thought to be the prime example of so-called plug flow, the emplacement of an ash flow, essentially a big wall of pumice and ash moving sluggishly together to fill a valley. This is an aerial view northwestward, and you can see the pink ash flow deposit all the way down the valley where it runs into Mount Kintolanat at the end. And this photo is in the lower valley that we were looking at, where you can see the pink ash flow deposit banked against the cross-valley moraine that stopped the flow and then diverted it around. The pink wedge is the very edge of the ash flow deposit against that ridge. And it's easy to see why it was first thought that it must just be one massive moving material. But by using the pumice proportions in the deposits, we can actually map the distribution of the different pulses of flow that came out of the vent to build, over time, the accumulation of the total thickness of the ash flow deposit. So the colors on these maps are the same as in that previous diagram. And the maps show, with the more circular distribution in the upper left, that the first all rhyolite flows, we call them package 1, were the most energetic. And as subsequent flows filled the old river valleys, each sequential flow package preferentially followed low areas where preceding flows had already compacted. So the Valley of 10,000 Smokes was not in place en masse, but rather was filled by 9 sequential pulses of ash flows. And by using the timing of the fallout at Kodiak, the fall stratigraphy, and seismic records, we know that these ash flows were all deposited in 16 hours. This is a classic flow unit contact in non-welded ignimbrite in Knight Creek, just above Three Forks, about 17 kilometers northwest of Novarupta. If you can squint your eyes, you can see the top lighter color has a fine-grained basal layer. That's package 4, and it conformably lies on top of package 3. So sometimes they're hard. The distinction between the packages is hard to see, but the pumice proportion counting made a big difference. Sometimes the differences in the packages are easier to see. The sequential flow packages sometimes cut shallow channels in the hours older ones, as on the left, where the dark matrix ignimbrite cuts the stratifications of the lower one. But on the right, you can see sometimes they accumulate with no scour at all, and all the stratifications are all parallel to one another. Well, these depositing currents, the ash flows, change with distance traveled. They change by densification, by deflation, increasing intergranular friction as they travel down valley. So the ignimbrite changes from turbulent to fluidized to sluggish grain flows, and it develops different kinds of things that are sometimes called flow units. So there's the laminations in the upper right, and the more obvious coarse and fine changes in the lower left. But these are not vent-derived flow units. These develop in response to the ash flows moving along the ground. So this is a conceptualization of what's happening at the vent. So remember the photo of the Pinatubo column. The ash flow cloud is actually density stratified. So as this cartoon shows, the more turbulent flow and lower particle concentrations are higher up. Well, these upper portions of the moving current leave deposits that look quite different from the more massive valley-filling ignimbrite. We call them high-energy proximal ignimbrites, HEPI for short. They're compositionally zoned also, just like the valley-filling ignimbrite. In spite of their stratified, wavy, and lenticular bedding, you can actually see at the bottom here the all-white 100% rhyolite, and at the top it's much darker because it has a whole lot more andesite and dacite in it. So although the deposits look very different and were deposited differently, they came out at the same time as what we were just looking at, as valley-filling ash flow. So this is Whiskey Ridge on the bottom left. It spans with about 400 meters relief above the present-day valley floor. The HEPI deposits on top of it, in the upper right photo, are about 5 meters thick. So the ash flow did not flow up the steep face of that ridge. This is one of the things that made it clear that the currents in placing these deposits, both the valley-filling ignimbrite and the HEPI deposits, the higher energy ones, were placed at the same time, but the current was density stratified. Well, while all this was going on, welding occurred right away. Welding and compaction happens most in the places of the ash flow where it's thickest, so in the central axial part of a valley-filling ignimbrite. This compaction in the axial parts of the ash flow sheet caused it to bend and even break along its margins. This is called the hinge line. This compaction and welding began immediately after emplacement. And we saw that in the channeling of the flows on those maps of the packages. Okay, well, we've talked about episodes 1, 2, and 3. And these explosive episodes were followed by extrusion of 3 lava domes. Compared to the explosive violence of June 6th through 9th, the growth of these domes wasn't much more than an afterthought of molten lava, sort of like toothpaste out of a tube. It was largely rid of its former gas content, and it slowly squeezed out of the vent. And although the exact timing isn't known, these domes likely formed within days, maybe as long as a year, after the Plinian events. But everything was already set by the time Briggs found it in 1916. There was one small dacite dome that plugged the episode 3 vent, but it was destroyed by small explosions. We call it the phantom dome because the only thing that remains of it are lava blocks like the one in the upper right that's scattered around on the surface on top of layer H. The same vent was plugged again by the rhyolitic Novarupta lava dome, which survives today. And the third one is a dacite lava dome extruded on the floor of Katmai caldera. It was the only new magma that came out of Katmai caldera in 1912. It was photographed by Griggs in 1916, which is a good thing because it's now covered by a couple hundred meters of water. Well, there are many aspects of the 3-day eruption at Novarupta that focus scientific attention on this remote volcano, and it's become one of the most intensively studied in the world. One of the foci, of course, were the 10,000 smokes themselves, which led to a number of pioneering studies. Griggs and his team were quite wary of these fumaroles at first. But by 1919, they positioned their camps to take advantage of the heat. And of course, no BTTS story is complete without this geologist, Father Hubbard, who in 1929 explored the valley with 4 young college boys and 2 dogs. But on a more serious note, Sayre and Hagelbarger they were students of Griggs at Ohio State University, joined Griggs' team, and they measured the fumarole temperatures as hot as 645 degrees C. That's nearly 1,200 degrees Fahrenheit. Studies of the mineral deposits around the fumaroles were important in understanding the high temperature vapor transport as it applied to metallic ore deposition, an important topic of debate at the time. So Terry Keith also continued in that tradition and made a lot of progress in studying those colored deposits there. The fumaroles in the ash deposits persisted for about a decade. Those closer to the vent lasted a little longer. There were still warm spots when I went to the valley first in 1980. But now all that's left of the smokes of these so-called fossil fumaroles are the brightly colored mineral deposits along the linear cracks where the steam once rose in the consolidated ash flow deposits, and the aureoles of color around where steam vents came out of the fallout. Well, there are many other lessons to be learned from a century of studies at Novarupta, but one of the last ones for today that I wanted to share is one of my favorites because it requires bringing together many things all at once. Things we've already looked at today, combined with earthquake records, to understand better how calderas collapse. So the reasoning goes like this. We combine what we know about the fall stratigraphy, layers A through H on the left, with the ash flow stratigraphy, the 9 flow packages on the right, and we tie them together with their pumice type proportions. And we've learned that the fault deposits here along Shellicott Coast erupted at the same time as the ash flow deposits here in the Valley of 10,000 Smokes. And we combine what we know about ashfall timing at Kodiak along the bottom of the slide and compare that timing with earthquake records. And the major earthquakes are shown by the red stars. There were many earthquakes associated with the eruption, beginning about 5 days before the ash started falling. The first major one, though, was just before midnight on June 6th, about 11 hours after the eruption began, and that marked the onset of caldera collapse. Now, one more piece of evidence we need, and we call it the Katmai Mud Layers. Although no new magma came out of Katmai in 1912, there were explosions that accompanied caldera collapse. Several muddy, block-rich layers expelled during those explosions are found in between the fall deposits, layers A through H, that came out of Novarupta. So on the right is an exposure of such a layer, about 12 meters thick, right on the rim of Katmai caldera. These explosion layers thin away from Mount Katmai, whereas the fall layers A through H thin away from Novarupta. The size of the blocks in the deposits gets smaller away from their respective sources too. So that's what's shown at the top The lithic blocks that came out with explosions from Katmai get smaller away from the caldera, and the blocks ejected with fall layers A through G get smaller away from Novarupta. The mud layers from explosions at Katmai coincide with earthquakes as the caldera collapsed piecemeal. So as Novarupta exploded and Katmai collapsed, there were 14 earthquakes of magnitude 6 to 7 felt in the area. So because we can see the Katmai layers interlayered with the Novarupta fallout, we know that the Katmai caldera collapsed fitfully as the magma beneath it erupted at Novarupta. These Katmai explosions and the ground shaking and all that collapse triggered a lot of landslides and debris flows. And stratigraphy is a powerful tool. This is a complete airfall sequence. Sublayers of B, a rhyolite debris flow, and the topmost layer B. So these two layers, B2 and B3, sandwiched a rhyolite debris flow that we know came out at the onset of caldera collapse because of the timing of the earthquakes of the earthquake patterns. Well, rhyolite is rare in arc eruptions in general, and there are no other quaternary rhyolite eruptions on the Alaska Peninsula except for one other. That came from Mount Katmai 23,000 years ago. So, although there's been speculation that the 1912 rhyolite might have been stored somewhere other than Mount Katmai, there's a list of things that favor a common reservoir under Katmai for all three magmas: the rhyolite, the dacite, and the andesite. And I decided not to show a bunch of chemical diagrams for today, but basically the chemistry of the 1912 products don't match Trident. There was no magma chamber underneath Novarupta. It cooled too fast. There's no collapse. There's no resurgent uplift. The rhyolite came out first. It's more buoyant than the others. And the rhyolite is very crystal poor. The only way you can keep such a large amount of rhyolite crystal poor if it's near an adjacent heat source. It's in thermal continuity with the dacite and the andesite. It's been shown by iron titanium oxide temperatures. Experimental petrology that Michelle and others have done shows a similar shallow pressure for all three magma types. And the dacite glass melt, if you were to take a magma with a lot of crystals in it and squeeze out the liquid, you would get a melt without the crystals. So if you look at the melt in the dacite and the melt in the rhyolite, they overlap in their compositions. This is true for major elements and trace elements. And it's also true for, there's isotopic overlap and continuity between all three. So we've learned a lot over the 100 years, and a lot of people have contributed. So thanks.
Any questions at this time for Judy?
Do you bring any samples of animals?
I didn't think to do that, actually. Do you have any samples?
I do. I can bring it tonight. I didn't think to bring it today.
Ah, okay. Yeah, Sandy Thomas is pretty cool. And actually, it's my hunch that looking more carefully at the banded pumice and exactly, well, we've looked at it some, but looking at it more, where it comes in, whether you get the rhyolite and the andesite, or rhyolite dacite andesite, or andesite dacite, and looking at when that comes and the timing of the whole thing, it might hold some perspectives for the storage of underneath.
Can you draw any inferences from your study as to what's going on with the Yellowstone dome right now in the caldera building on the other side?
I'd say only in generalities. Each volcano is its own beast, so to speak. That one's much big. Has been much bigger than Novarupta by several orders of magnitude. Have you seen the movie Super Volcano? Well, that's actually a pretty good one, and it shows the impact of of that kind of eruption. I mean, Novarupta, we can draw that kind of analogy, but Novarupta would just pale in comparison to any explosive eruption. I don't think we can say whether the dome's going to continue or whether it's going to stop or whether something more is hiding behind it. Huh?
Judy, could you speculate at all about the nature of the crustal or subcrustal plumbing? It's not a fair question, I guess, but geez, you guys have been in there a long time, and you must have some ideas. Between the system under Katmai itself and Novarupta, the sill and all that.
And I have a related question that you can maybe answer at the same time. What did the valley floor look like prior to the eruptions, where the Novarupta vent was? And then, was there anything that would have foretold that was going to be the vent? What's the distance from Katmai to a couple kilometers?
It's 10 kilometers.
10 kilometers, yeah.
Okay, so start with this.
It relates to Tom's question.
Yeah, we'll start with this cartoon of what you were asking about. This is the conceptualization. So you have the red rhyolite and the yellow dacite and the green andesite stored underneath Mount Katmai with most likely configuration would be a horizontal sill rather than a dike, because it would probably follow the lines of weakness, which are the horizontal bedding planes of the Naknek sedimentary deposits there. Other than that, no one's been very successful yet, trying to image these sorts of things, but that's the best guess. And it's the chemical argument that is the one that makes it look like it's all under Katmai. As much sense as it doesn't make. But that's the way it is. And as for what looked like around the vent, it was anyway, if you look at pictures, let's see, do I have a picture? Well, the closest I can get is there. You're actually on the turtle here, the ejector ring, looking over at Bake Mountain, which is just to the north of the vent. And you can sort of see those spurs coming out. They were probably, that's the caldera wall, essentially, but some portion of that might have been already truncated by glaciers, because it was a glacial valley that curved around from Trident and curved around to the river Leppy, drained into the river Leppy. So there was, other than that, we don't really know, but there was likely some amount of glacial valley carving.
But no constructional feature of any kind, no other event.
Well, not that we know of. The area was not very well known. Only some of the early people who went across the pass went through and described things, but they weren't really looking at that kind of thing. All we know is it looked a lot like other valleys on the other side.
So Judy, the rhyolite that you said erupted much longer ago from Katmai, what sort of eruption was that like?
It was a fuming eruption. Oh, it was. There are deposits left, and there are not very many left because it's been glaciated. So there are only a few patches on both sides of the crest, and they're thick enough that and coarse enough that it looks like it was bigger than 1920. It was not high silica rhyolite. It was 72%, 73, but it's still rhyolite. So
So it's pretty obvious from the pictures that you show that there isn't much basement peeking through, but in the bigger picture regionally of the location of all the different vents, is there any kind of pattern, like they were lining up on structures or faults or anything that would have controlled the plumbing system in any way? Or is it you think it's just horizontal flow along the permeable magnetic sandstones or something?
Well, that seems to be the most likely thing. There's no other. I mean, it's an arc, and so,
yeah.
but that's what the big stratovolcanoes show. So aside from that, there's been no other real evidence. People have looked geophysically at faulting and things for some sort of surface expression of what this might look like between the two, and there's been nothing definitive.
One thing I appreciate from your talk is the large volume of material that came out. The question I'm curious about is, what's the significance of this material over the last 100 years as a sediment source?
Oh,
in terms of, so if you took the modern topography and subtracted the isopachs, what volume of that has since been eroded and redeposited elsewhere?
Oh, I don't know. But what I can tell you is that things started, of course, remobilizing immediately. You can see by the debris flows, there were landslides. There were several things. There were pumice rafts, pumice like this, that were washed out to the Shelikof Strait, and the pumice was mostly washed out there. And those pumice rafts were floating around for at least 2 decades. So there was a lot of it. If you go down to the area by Katmai Bay, which is on the Shelikof Strait side of the vent, and you try to cross McGee Creek there, you'll find it's sort of like quicksand, because it's a very shallow, braided sort of a river delta full of pumice mesh, and that continues to wash down from the side slopes. So there's a lot of remobilization. What the volume is, I don't know, but the volumes that we calculated are, well, they're just from intact deposits. There's still plenty of it left. I mean, I don't think that half of it has been remobilized.
Do you think something the same size could happen there again, and if so, how soon?
I should point out, this is our state emergency management.
Now that's good enough. Couch my words. Yes, I think something could happen again. I think Katmai's erupted explosively several times, and of all the volcanoes in that area, Katmai's the one that has erupted explosively more than any of them, and erupted in a big way. There was another big bayside eruption from Mount Katmai between 12 and 16,000 years. I didn't mention it because it's not rhyolite, but it was pretty big. And so the chances of another eruption happening there, an explosive one, are pretty good. Whether it would happen in our lifetimes, I think the chances are probably small. And that's where ABO comes in. These guys do a great job monitoring things, and most of the time, not always, there are precursors, seismic precursors. So hopefully we wouldn't be caught totally off guard. I couldn't really answer it any better than that.
Thanks.
Do you have any other research questions that you'd like to tackle?
I don't know where I can start. You mean here?
Yeah.
Well, one of the things that I'm in the process of doing is we're looking at those high energy proximal flows. No one's really done a lot of work on that kind of thing before, and I didn't even touch on a lot of the work that we've done with the proximal deposits. So we've looked very carefully at the near vent deposits, all these hybrid things, as well as these high energy flows that plaster the ridges. So we've done a lot of sieving, grain size work, compositional counts, and we're in the process of writing that out now. The next thing that we were thinking about doing was to try to address we have this timing sequence using both earthquake records and the ash flow. What we're thinking is if we look even more carefully, maybe we could get the timing sequence down to tens of minutes. So that's a possibility. Aside from that, I think I spend enough time in the Valley of 10,000 Smokes, and I have about half a dozen other things going on at the same time.
One question, I was curious about the segregation of magmas in that model, with apparently no formation of crystal cumulates or anything like that. Is it just purely a density stratification of some kind?
Well, the rhyolite, first of all, is very crystal poor. It has on the order of 1 to 3% crystals. The dacite and andesite, however, has 35 to 45% crystals. There's a lot of crystals. So there's your crystal cumulate. And there are things erupted as sort of as lithics or recycled ejected that were even more crystal rich than that.
So I understand you've been working on the recent Chitin deposits in Chile?
No.
No, I thought you've been down in Chile.
I have been in Chile and Argentina, but not on Chitin.
Not on Chitin, okay.
Laguna del Maule.
Oh, okay. So I was going to say, I was wondering how that compares in scale to this one, if you had any knowledge there.
Oh, much smaller.
Yeah.
There's no comparison. I mean, the effects are much greater because it's the ash has closed a lot of airports. So, but
perhaps we could get one more question in, and then I just have some brief comments afterwards, just to remind folks of the time.
I didn't understand the source or the mechanism of the mud layers near Katmai. Could you explain that just a little bit?
The source of the mud layers?
Yeah, and the mechanism of them placing.
As Katmai collapsed, there were explosions at the same time. So those mud layers are basically sort of a combination of mud and lithic layers. Maybe mud is not really a very good term for it. There's a muddy matrix with lots of lithic blocks in it. And it's just basically an explosion with no new magma coming out. So
was it wet, Judy?
Yeah.
So it was the parent rock, or source rock of...
That's right. It was Mount Katmai, pre-existing Mount Katmai, that are the blocks in that block and mud layer, or layers. So as Katmai certainly exploded. There was certainly explosions, and there were fumaroles all around it and on the floor, which is why they thought that Katmai was a vent, because it certainly looked like it was a vent.
So there was a fairly active hydrothermal system in Mount Katmai.
It was and may still be. I mean, the lake hasn't frozen. Maybe it freezes over now, but the last time I was there, the lake still doesn't freeze over in the wintertime. And that's a deep lake. So there must be something hot down there.
Was there a lake there before the eruption? Was
We
there
don't
a crater or something?
Well, there are reconstructions of the peak, and it looks like it was a double, sort of a double peak. There was a Coast Guard survey done, I forget the year, and from that, the profile of Katmai was reconstructed. So there might have been a little crater, but there wasn't it wasn't a really big one, maybe a small one. And it certainly lost. Do you remember it? It lost at least 1,000 feet, maybe more.
Okay, well, I want to thank everyone for coming, and again, thank Judy for I just want to mention very quickly, we do have handouts if you're interested and want more information. We do have a public lecture tonight at the museum. We also will have this summer at the Alaska Public Lands and Information Center multiple lectures on Katmai and other volcanoes. There's lots of events going on. This is the kickoff of the commemoration of the 100-year anniversary. Please check the ABO website as well as the National Park Service, because this presentation was in partnership with them as well as the Alaskan Historical Society. So if you have any questions, if you received my email from Yvette Gillies, please contact me, and there's cards up here as well. So thank you very much.
Thanks for coming, everybody.